Now to find the moment of inertia of a uniform rod about perpendicular bisector. Suppose this is the rod of length L and mass m. This is the length L and m is the mass of rod. That means its mass density or linear mass density is m by L. We have to find the moment of inertia about the perpendicular bisector. That means this axis is passing through the center and perpendicular to the rod. Because mass is in continuous distribution, so we have to use method of integration to find the moment of inertia, and di we can write it as dm into r square or x square. We take this as reference. That means this is if 0, this is L by 2 and this is minus L by 2. This is the x equal to minus L by 2. This is x equal to plus L by 2. To use the method of integration, we take an elementary length so that we can have a elementary mass. So this elementary length is at distance say x, and the length of this elementary part is dx. So dm, that is the mass of the elementary length, dx is mass density multiplied by the length of elementary part. So it is m by L into dx. And we have to use this formula. It is equal to integral dm is m by L into x. M by L into dx. And then x square. And where we have to integrate this from minus L by 2 to L by 2. It will give the term which is constant will be taken out. It is m by L, and remaining will be remain inside the integral minus L by 2 to L by 2, and this is x square dx, and it is equal to m by L into. Now using the integration of x square, it will come x cube by 3, and limit is from minus L by 2 to L by 2. 3 is constant term, it will be taken out, so it is m by 3L, and then put upper limit L by 2 whole cube minus, then put lower limit minus L by 2 whole cube. It is equal to m by 3L, and opening this bracket, it will come L cube by 8 minus L cube by 8. Opening the bracket, this minus become plus, and we get 3L L cube by 8 plus L cube by 8. Adding, it results in L cube by 4. 1 L we cancel, so it will be L square. That means 3 into 4, 1 by 12. 1 by 12 m L square. That means moment of inertia of a rod about its perpendicular bisector, moment of inertia about perpendicular bisector will be 1 by 12 m L square. Important formula to be memorized. Similarly, using the parallel axis theorem, we can find the moment of inertia about the end of the rod, which is parallel to the perpendicular bisector. For that, suppose this is the rod of length L. This is the center and perpendicular bisector passes through it. This distance is L by 2. And this is A, suppose this is O and this is B. And now we have to find the moment of inertia about this axis passing through B, which is parallel to the perpendicular bisector. So here we use the parallel axis theorem. Parallel axis theorem say I equal to I naught plus md square. Means I naught is the Moment of inertia about the axis passing through the center of mass. I is the axis parallel to this axis through which we have found the I naught. M is the total mass of the rod, and D is the distance of the center of mass from the point through which axis is passing for I. So I naught we have already found. For the rod it is 1 by 12 ml square. So we put here it is 1 by 12 ml square plus mass is m and distance is, this is d. So d is L by 2 square. So it is equal to 1 by 2 ml square plus 1 by 4 ml square. Taking LCM, it becomes 1 plus 3 ml square. 1 plus 3, 4 will cancel out. It will come 1 by 3 ml square. So it is the moment of inertia about the axis parallel to the perpendicular bisector and passing through the end of the rod. So these are the two examples which we have discussed for the rod. One more case we will take in which mass of the rod is not uniform. These two cases we have taken here are mass is uniform, mass distribution is uniform. Mass distribution is till this case we have taken all the cases in which uniform mass distribution. But now we take one more example of the non-uniform mass distribution in which mass may change as per the length. Suppose mass is changing with x. This example we are taking now.